Oxidation in organic chemistry typically involves the insertion of oxygen or the removal of a hydride moiety. Hence, an alcohol may be considered oxidized if it is transformed into an aldehyde. An aldehyde can still be oxidized by insertion of an oxygen at this position to form the carboxylic acids. The first example of oxidation of alcohols is the cleavage of 1,2-diols or vicinal diols with sodium periodate. The vicinal diols break to form aldehydes and ketones. For example is this compound. I numbered its carbon here to guide you in identifying the cleavage points of this reaction. When sodium periodate acts on this molecule, this bond in between the two hydroxyl groups will break, and a keto group will form on this side, while on this side, an aldehyde will form. Similar to ozonolysis, the products of this reaction can also be used to identify the starting material, such as in this case. Can you identify compound A based on the structures of the products of this reaction? The structure of A is this one. Here you just need to consider that these two carbonyl groups are connected in the starting material. Previously, there is a hydroxy group here and a hydroxy group here, such as this compound. Treatment with sodium periodate readily cleaves this bond to give these compounds. In contiguous triols, the middle alcohol becomes formic acid. If you consider this compound, cleavage of the bond here will give propionaldehyde or propanol. Cleavage of this bond here will give you formaldehyde. The middle carbon will be transformed into formic acid. If this is a carbonyl group, and this carbonyl group is flanked by OH groups, this will be converted to carbon dioxide upon cleavage of these two bonds. Cis-diols react more rapidly than trans-diols. This can be explained by the mechanism of this reaction, but this topic is beyond our course. Aside from sodium periodate, treatment with periodic acid and lead tetraacetate also give the same products. The common type of oxidation of alcohols depend on the presence of alpha protons. These are protons that are geminal to the hydroxy group. Aqueous potassium permanganate and potassium dichromate or sodium dichromate or chromium trioxide in sulfuric acid convert primary alcohols to carboxylic acids and secondary alcohols to ketones. In this example, potassium dichromate in sulfuric acid readily converts this secondary alcohol into a ketone functionality, and this primary alcohol into carboxylic acid. In both these cases, the alcohol has alpha protons present in this carbon and also in this carbon. Pyridinium chlorochromate or PCC converts primary alcohols only to aldehydes and secondary alcohols to ketones. The structure of PCC is this one. For example, using the same compound used earlier. PCC with dichloromethane solvent forms a ketone here and an aldehyde here. The aldehyde is no longer converted to the carboxylic acid. Because tertiary alcohols do not have alpha protons, they cannot undergo this type of oxidation reaction. PCC is formed when chromium trioxide is dissolved in hydrochloric acid and then treated with pyridine. PCC oxidations are usually done in dichloromethane. Dichloromethane can be dried very easily, and dry solvents do not have water. This is to avoid the formation of the aldehyde hydrate, which is important in the formation of carboxylic acids. Chromate oxidations rarely affect double bonds. In this example, only this hydroxy group is affected, and this is converted to a ketone functionality. This double bond is untouched. If potassium permanganate is used, this double bond will be broken to form carboxylic acids on opposite sides. Chromium trioxide in sulfuric acid can differentiate primary and secondary alcohols from tertiary alcohols. Take note that tertiary alcohols cannot be oxidized by this reagent. Chromium trioxide is usually orange, and upon reaction with primary and secondary alcohols, it will form a greenish cast, providing evidence of oxidation.